Welcome to Bisectors of Triangles. Today's objectives are to prove and apply properties of perpendicular bisectors and to prove and apply properties of angle bisectors. So let's start out with the Circumcenter Theorem. Now, if we have a triangle, we know that a triangle has three sides. If it has three sides, it also has three perpendicular bisectors. Three of these are perpendicular bisectors. Now, these perpendicular bisectors intersect at some middle point right here. Lines that intersect are known to be, we're going to call them concurrent. So this point here, we'll call it point A. We'll say that A is the point of concurrency. Now there are different types of point of concurrencies, and they're specific to what you're talking about. So here we're talking about perpendicular bisectors. So when you have perpendicular bisectors that are intersecting, that are concurrent, we call that point of concurrency the circumcenter of the triangle. So the circumcenter is specific just to perpendicular bisectors. The circumcenter of the triangle. That's specific to perpendicular bisectors. So now that we've established some vocabulary for circumcenters and perpendicular bisectors, we want to look at the theorem. Now the Circumcenter Theorem tells us that the point of concurrency for perpendicular bisectors is equidistant from the vertices. So let's write that out and then we'll draw it on the picture. So the circumcenter of a triangle is equidistant from the vertices. So if we have our point A here, and we'll call these corners B, C, and D, these vertices of the triangle, the length from here to here, from here to here, and here to here is all the same. So the length of AB is congruent to the length of AC, which is congruent to the length of AD. And that's the Circumcenter Theorem. Now the location of the circumcenter can be either inside, outside, or on the triangle. So location can be inside, outside, or it can be right on the triangle. But this depends on what type of triangle we're talking about. So let's look at an acute triangle. Now remember, the circumcenter is the point of concurrency for the perpendicular bisectors. So I have to draw three perpendicular bisectors. There's one, here's another one, and there's a last one. So this point of concurrency, or this circumcenter, is inside the triangle. Now how about an obtuse triangle? So we have to draw an obtuse triangle that has one obtuse angle. Now let's think about the perpendicular bisectors. So if I come to this point and find the middle line right here, and I draw a perpendicular bisector, it has to go through like this. Then for this bottom line right here, the midpoint would be right about there. So this perpendicular bisector will go up this way. And finally for this side, here's this point, which is in the middle of this line, and if I draw that perpendicular bisector, it'll come here. So we can see that these points intersect somewhere outside of the triangle. Now let's look at a right triangle. So we need a right angle, and let's draw perpendicular bisectors. So for the hypotenuse, here's the middle point, and it goes right through there. For this side right here, the middle point will be right about here. So it'll go down through there, and the perpendicular bisectors will come through here. So the location can be either inside, outside, or on the triangle. Another term we want to familiarize ourselves with is what a circumscribed polygon is. So here, this triangle is circumscribed within this circle. So we say a circle that contains all the vertices of a polygon is circumscribed around the polygon. So we would say that this circle is circumscribed around the polygon. So it means it's going around all the edges of the polygon. And we say that this point P, which is the circumcenter of triangle ABC, this is also the center of the circle. Let's use our knowledge of perpendicular bisectors to help us find the following lengths. So segment KZ, LZ, and MZ are the perpendicular bisectors of triangle GHJ. Let's first find the length of HZ. So HZ is this segment right here. But we know that KZ, LZ, and MZ are the perpendicular bisectors. So let me just highlight these in blue. So KZ, LZ, and MZ, these are all perpendicular bisectors. So this point here is the point of concurrency, or the circumcenter. Now the circumcenter is equidistant from all the vertices. So the length of HZ has to be congruent to the length of ZH, which has to be congruent to the length of GZ. So if we know any of these lengths, we know all the lengths. Well, we know that GZ is 19.9, so HZ has to be 19.9 as well. Now for number 2, for GM, that's this length right here, and since MZ is a perpendicular bisector, this segment has to be congruent to this segment. So GM is 14.5. Look at number 3, GK. Now GK is this length right here. Once again, these are both perpendicular bisectors, so this segment right here has to be congruent to this. So GK would be 18.6. For number 4, JZ. JZ goes from the vertex right to the middle. So that should be the same as GZ and HZ. So it's 19.9. Now let's find the circumcenter of a triangle. So we're going to find the circumcenter of triangle RSO with the following vertices. So let's draw the first point. So point R is at negative 6, 0. So that's our point right here. Point S is at 0, 4. So 1, 2, 3, 4. Here's point S. Here's point R. And point O is at 0, 0, right at the origin. So here's our triangle. So we remember that the circumcenter is the point of concurrency for the perpendicular bisectors. So our game plan is to just draw the perpendicular bisectors and find the equations for them. So if I want to find the bisector for this line here, I know this length is 6. So if I'm splitting 6 in 2, I have to get to 3. So here's a first, second, and third point. So this line is going to be a straight line through this point. And the equation for this line is x equals negative 3. Now this is a right triangle, so I know that the circumcenter is going to be right on the triangle. So when I go to segment SO, I know this whole length is 4, so half of it has to be 2. So I draw my point right here at 0, 2, and I draw my perpendicular bisector. Now I already know that these are going to all intersect right here. So all I have to find is what that point is, which is pretty easy. I just count over. And it's negative 3, 2. So this is the circumcenter of triangle RSO. We talked about the point of concurrency for perpendicular bisectors. Now let's talk about the point of concurrency for angle bisectors. So if we have a triangle also has 3 angle bisectors. So that's bisecting this angle here. This is bisecting this angle here. And this is bisecting this angle here. Now this is different than the perpendicular bisectors. These are the angle bisectors. Because it splits those angles into 2 congruent angles. Now the angle bisectors also have a point of concurrency. But we have a different name for that. The point of concurrency for angle bisectors, we refer to that as the incenter. So for perpendicular bisectors, it's called the circumcenter, and for angle bisectors, it's called the incenter. So here, let's name the incenter point A, and let's name these points B, C, and D. Now the Inscribed Theorem tells us that the incenter of a triangle is equidistant from the sides of the triangle. So the incenter is equidistant from the sides of a triangle. This is different from the perpendicular bisector. The perpendicular bisector was equidistant from the vertices. The point of concurrency for angle bisector is equidistant from the sides. So that means that here in my diagram, the length of AB is congruent to the length of AC, which is congruent to the length of AD. The location of the incenter is different than the location of the perpendicular bisector's point of concurrency. So for the incenter, it's always inside the triangle. So regardless of what type of triangle it is, here let's have an acute triangle. Now if these are all angle bisectors, and I realize that for the acute angle triangle, it looks very similar to the perpendicular bisector one. But for acute, it's always on the inside. Now let's look at an obtuse one to get a better idea of what this is like. So the angle bisector here, this splits these two angles. So that one looks similar to the perpendicular bisector one. But when we go from this vertice right here, these angles are congruent here. And when we go from this angle here, these angles are congruent here. So this one's inside as well, and that's an obtuse triangle. And for a right triangle, same. This splits that angle, this splits that angle, and this splits that angle. So for incenter, it's always inside the triangle. And this is a right triangle. So the incenter is the center of the triangle's inscribed circle. So if you had a triangle and you drew a circle inside of that triangle, the middle of that circle would be the incenter. So we say a circle is inscribed in a polygon if each of its points intersect one time with a side of the triangle. So we want to know the incenter is the center of the triangle's inscribed circle. And it's inscribed if it touches exactly at one point. Let's look at two angle bisector problems. JV and KV are angle bisectors of triangle JKL, and we want to find the measure of each of the following. So the first thing we want to find is the distance from V to KL. So we want to find the distance from here to here. Now when they say distance, they're talking about the shortest distance. So let's look at point W and V. Now the point from V to line JK is demonstrated right here. This is the shortest point from V to KJ. So what we're looking for is the perpendicular segment from here to here. So that'd be this point right here. Now, by the Inscribed Theorem, all these points to these lines are congruent. I could draw another one right here, and technically all of these segments should be congruent. So this is 7.3, and this distance is 7.3 as well. Now let's find the measure of angle VKL. Now since these are all angle bisectors, and if this angle right here is 19, I know this one here as well has to be 19. This whole angle here is 19 times 2, or 38 degrees. So now I have this angle figured out. I know this angle here is 106. What I'm trying to find is the measure of VKL. So VKL is just this angle right here. So if I add up 106 and 38, get 144 degrees. So I know that there is 180 minus 144 degrees left here. So let me just subtract those two, and what I'm left with is 36 degrees. Now, since point B is the incenter, I know this entire angle here that I circled is 36 degrees, but I just want half of that. So I split that in two, and I'm left with 18 degrees. So once again, since this angle was 19, and these are angle bisectors, that means the other side of it had to be 19 as well. I added those together, I got 38. I knew this angle here was 106, so if I added up 38 and 106, I got 144. I know the sum of the interior angles of a triangle are 180, so I subtracted 180 from 144 and got 36 degrees. This whole angle here was 36, but I had to divide it by 2 to get 18. Let's look at some planning. So for the 4th of July, the towns of Ashton, Bradford, and Clearview will launch a fireworks display from a boat in the lake. I want to draw a sketch to show where the boat should be positioned so that the distance from all the towns is the same. Okay, so we have 3 points, so we can easily draw a triangle. So from here to here, from here to here, and then we can connect Clearview and Bradford. So looking for some central location. So if they're looking for some central location, they want to find a point that's equidistant from the towns. Now the towns here aren't on the sides of the triangle. The towns are the vertices. So that means we have to draw perpendicular bisectors and find the circumcenter. So I'll go to this point here. That would be the middle, and if I draw, let me draw this in black, a perpendicular bisector. There's one for the middle of this next point. It's right about here. And for the last one, the intersection is right somewhere here. So there's no exact point or measurement that I wanted. All I want here is for you to justify your sketch by pointing out. So this here would be the center point for all of these. Alright, and that's the end of our video. I hope this was helpful. Thank you. Take care.